So you should have watched the video already about what kind of stationary points exist. In this video, we're going to actually go through an example and classify the nature of the stationary point without a graph. So let's have a look. Example, find the stationary point for this function y equals x cubed plus 6x squared minus 15x plus 2, and then determine, in other words, classify the nature of each stationary point that you find. Okay, so the first thing we need to do is differentiate the function, because remember, if we differentiate the function, that gives us the gradient function. So differentiating that function gives me 3x squared plus 12x minus 15. Now, because I want to find the stationary point, I'm going to find out where does the gradient equal 0. So in other words, I'm going to put my gradient function equal to 0 and solve it to find what the x value is. So we're going to solve this. You'll notice it's a quadratic. We should be familiar with solving quadratics. I'm going to factorize. Before I factorize, I can see they all divide nicely by 3. So I'm going to divide through by 3 first to make the numbers smaller. Leave me with x squared plus 4x minus 5. Then I'm going to factorize. So factorizing, I'm looking for the two numbers that multiply together to make negative 5 and that add together to make 4, x minus 1 and x plus 5. Using the null factor law, we can see that either x minus 1 equals 0 or x plus 5 equals 0. And solving each of those individually gives me the 2 points for x where the gradient equals 0. That means we have two stationary points. There's one at x equals 1 and one at x equals minus 5. We need to find the coordinates. I think the question asks us to find the stationary points, so that's a coordinate. Because we have the x values, let's do the right thing and find the y values. So when x equals 1, first of all, to find the y coordinate of this, I obviously go back to the original function, which was y equals x cubed plus 6x squared minus 15x plus the 2. So let's sub in when x equals 1. So subbing in when x equals 1, if I work this out right, hope I don't make a mistake, I get y equals minus 6. Let's do it when x equals negative 5. So when x equals negative 5, probably haven't left myself enough room. Let me just move that. Okay, I'm moving it down here, sorry. When x equals negative 5, I'm going to do y equals negative 5 cubed plus 5 times negative 5 squared minus 15 times 5 plus 2. Working that out gives me minus 125 plus 150 plus 75 plus the 2. Y equals 102. Now we have a stationary point at the point 1, minus 6 and a stationary point at the point minus 5, 102. Now part B asked us to determine the nature of each point. So we're going to look at the left of each point and we're going to look at the right of each point to be able to classify the stationary point. So I've written down here that I'm looking at the x value either side. Let's just remind ourselves the stationary points occurred at x equals negative 5 and there was another one at x equals 1. So you can pick any values as long as it's to the left and to the right of each point. So I'm just going to go with negative 6. Try and make the values as easy as possible. 0 is an easy value to use that's either side of those, and then obviously I'm going for 2. Now in each case I need to work out the gradient at each of these x values so I can look. Now I already know the gradient at negative 5 is 0 and I already know the gradient at 1 is 0. So now I'm going to use the gradient function, which was dy dx equals 3x squared plus 12x plus 15, and I'm going to substitute each of these values in. So let's first of all look at when x equals negative 6. So let's look at the gradient. 3 times negative 6 squared plus 12 times negative 6 minus the 15 is 108 minus 72 minus 15. The gradient is 21. That is a positive gradient. Okay, it's really important to identify what the sign is. So that's positive. So I'm going to write that result in my table. So I've got the value of 21 and I know it's positive. So I'm going to draw a positive line. Okay, now that kind of already indicates what kind of stationary point it might be. So now let's look at when x equals 0. So when x equals 0, let's do dy dx. Dy dx equals, so it's 3 times 0 squared plus 12 times 0 minus the 15, which gives me a negative 15. That is a negative gradient. Oops. A few problems there with my board, negative. All right, so go back up to the table. I'm going to fill that result in, negative 15, and put a negative. Now I can already see this has formed a maximum shape. Therefore, I know that at the stationary point when x is negative 5, it's a local maximum. Okay, so we can say that. Now let's look at the other scenario which we had was x equals 2. So when x equals 2, the gradient is, substitute the values in, so 3 times 2 squared plus 12 times 2 minus 15 equals 12 plus the 24 minus the 15 equals 21. And that is a positive number, so therefore it's a positive. So let's have a look at what that will give us at the table. So a positive goes like that. So we can see that at the point when x equals 1, we've got a local minimum. So I'm just going to summarize that information. And it really is important to summarize the information like this. Now, that's pretty much it, but I am going to go through a second example, which is just harder factorizing and involves fractions. So at this point, you can probably stop the video and answer some questions, and then you can come back to the video. Just make a note that we're at about 6 minutes. Okay, example number 2. Find the stationary points on the curve y equals 4x cubed plus 3x squared minus 6x minus 1 and classify the nature of the stationary points. So let's firstly differentiate the function, because remember, differentiating finds the gradient function. So we're at 12x squared plus 6x minus 6. Now, I'm going to let dy dx equal 0. And that's because if the gradient is 0, that will tell me the value at where the stationary point is, the x value of where the stationary point is. So 0 equals 12x squared plus 6x minus 6. Now I need to factorize this. I can see that all the numbers divide nicely by 6. So I'll make it easy for myself, making it 2x squared plus x minus 1. Now, factorizing when the value of a is greater than 0. So I do this I don't use the cross multiplication method. I use it by breaking down the middle term, the b term, which is 1x, break that down into 2. And I also find those values by looking at the c term and going, right, I need two numbers that multiply together to make 2 times minus 1. That add together to make the coefficient 1 here. So those numbers must be minus 1 and positive 2. So now what I'm going to do is I'm going to break down this middle term into those two numbers and then individually factorize. So I keep the 2x squared there because it's just the yellow bit I've highlighted that I'm breaking up into plus 2x. So I'm using these numbers here, 2 and minus 1, minus 1. So those two there that I'm highlighting make up the yellow. And then I need to still carry down the minus 1. Now, you should be able to factorize this nicely by splitting it in 2. So looking at the first two terms, I'm going to factorize those two terms first. That gives me 2x, x plus 1. Now I'm going to factorize the last two terms. I'm going to bring out a minus 1 and I have x plus 1. And you should find that you get these two brackets the same. Now you can say that this term and this term are both multiplied by x plus 1, so therefore 2x minus 1 can be multiplied by x plus 1, and you've factorized it. Now looking at the brackets, let's use the null factor law to solve this. So we can say that either 2x minus 1 equals 0 or x plus 1 equals 0. So solving that gives me x equals 1/2. Or x equals minus 1. So we actually have two stationary points again. One where x equals 1/2 and one where x equals minus 1. Now, I should find those y coordinates. We can do that by subbing that back into the original equation. Now, I can do that by writing the equation down, which was 4x cubed plus 3x squared minus 6x minus 1. So firstly, let's do it when x equals 1/2. When x equals 1/2, and we get 4 times 1/2 cubed plus 3 times 1/2 squared minus 6 times 1/2 minus 1. Working all that out, you can use a calculator. You get minus 2 3/4. Now let's do the other one. Let's do when x equals, what was the other one I got? When x equals minus 1. When x equals minus 1, can easily work that out. Minus 1 cubed plus 4 plus minus 1 squared times the 3. When x equals minus 1, y equals 4. Okay, so our stationary points are, so a half, comma, minus 2 3/4, and then minus 1 and 4. Now, let's classify the nature of those stationary points. Looking at the x values, I've got a stationary point at minus 1 and a stationary point at a half. So remember, to classify, I need to look at the gradient either side of these. So I'm going to choose an x coordinate that's to the left of this. So I'm going to go with minus 2. And to the right, 0. And 0 is to the left of this one. So I'm going to go up to 1 to be to the right of that. And I'm just going to look at the gradient either side. So let's go, we know also, by the way, that the gradient at minus 1.5 is 0. So looking at the gradient when x equals 2. So when x equals minus 2. When x equals minus 2, the gradient dy dx, to remind myself what dy dx is, it was 2x squared plus x minus 1. So let's sub that in. 2 times minus 2 squared plus minus 2 minus 1. The gradient is 8 minus 2 minus 1 is 5. So we can say that that's a positive number. So I'm going to do a positive line. We already know that's 0, 0 line. Let's look at the case when x equals 0. So when x equals 0, let's look at the gradient dy dx. I'm going to sub in 0. So I got 2 times 0 squared plus 0 minus 1. That gives me minus 1. That's a negative number. So filling the table in, put a negative line. We can see that at the point when x equals 1, we've got a local maximum. Let's keep going. I'll do the 0 line there to look at the pattern. Let's look at when x equals 1 now. When x equals 1, just scroll up. When x equals 1, dy dx equals 2 times 1 squared plus 1 minus 1. The gradient equals 2. It's a positive number. So positive line goes up. We have here a local minimum. So when x is a half, that's a local minimum.